Tantor Audio, a division of Recorded Books, presents A World Beyond Physics, The Emergence and Evolution of Life by Stuart A. Kauffman, narrated by Bob Souer. Prologue. Classical physics, our gift from Newton, is our world written in the passive voice. Rivers flow, rocks fall, planets orbit, stars arc in the space-time deformed by their masses. There are no doings, only happenings, myriad, miraculous, but brute. I broach 78 years as I sit to write, having angled to the kitchen to pick out a nectarine to eat. Yesterday I clambered aboard the Poised Realm, my 22-foot boat, to skiff across to the crane dock on Orcas Island to drive to East Sound, Washington, to buy the nectarine I just retrieved as an afternoon snack. My heart thumps a bit, my own human heart. Most of my readers have a human heart as well. Just where did my human heart, the nectarine, my kitchen, the boat, and East Sound come from since the brute happening of the Big Bang 13.7 billion years ago? Since Newton, we have turned to physics to assess reality, what is real. But physics will not tell us whence we come, how arrived, why the human heart exists, nor why I can buy nectarines in East Sound, let alone what buying is. We will talk of these things, for there is more to know than we know, and more to say than we can say. We are in a world beyond physics. We are in a world of living creatures that construct themselves, yet we lack the concepts to say it. A tree, from a seed, builds itself, launches itself upward toward the sun. We see it and do not yet know what to say. A forest builds itself, rooted, branched, quiet, as if longing. Our biosphere, too, grows in diversity into what it can become and has done so for some 3.7 billion years. A giraffe? Who knew 3 billion years ago? None could have known. And nectarines? Who could then have said? We estimate that 50 to 90% of the 10 to the power of 22 stars in the known universe have planets cycling them. If, as I believe and will say, life is abundant, the universe is rife with becoming, based on physics, but beyond any physics we know. The concept of perhaps 10 to the power of 22 biospheres staggers me. Yes, we thrill at Hubble's image of billions of galaxies, some 10 to the power of 11 of them. But are there 10 to the power of 22 biospheres, ebullient like ours? Not a world beyond physics, but worlds beyond physics, as vast as the vastness of the physics we know, almost unknowable. We miss in our science the idea of a system that constructs itself. I will introduce the requisite concept due to Maël Monteville and Matteo Mosio called constraint closure. These young scientists have found or maybe the missing concept of biological organization. We will grow to understand it clearly and build on it. The ideas are a tiny bit complex, but not very. We will get to them. But for now we can think of constraint closure like this. It is a set of both constraints on the release of energy in non-equilibrium processes and those processes such that the system constructs its own constraints. This is an amazing idea. Cells do this, automobiles do not. Living systems achieve this constraint closure and do what are called thermodynamic work cycles by which they can reproduce themselves. Living systems also exhibit Darwin's heritable variation, so can undergo his natural selection, hence evolve. I've written about that in some of my earlier books, but I was nagged by a feeling that there was something missing. With constraint closure, a crucial puzzle piece is put into place. But what evolves cannot be said ahead of time. What evolves emerges pre-statably, I know of no better word, and builds our biosphere of increasing complexity. We are its children, as are giraffes, nectarines, and sea cucumber. Some years ago, at his 70th birthday fest, a physicist friend of mine smiled at the way biologists see the world. Were biologists with Galileo on the Tower of Pisa, they would have dropped red stones, orange stones, pink stones, blue stones, green stones, and so on. My physicist colleagues chuckled knowingly. Physicists seek to simplify to find laws. Biologists study how life became complex. So, of course, the red stones were giraffes, the orange stones nectarines, the blue stones sea cucumbers, and the green stones, well, just us. The question is not whether the sea cucumber, giraffe, us, or the nectarine falls faster, but where did they come from in the very first place? Physics won't say. No one knows. There is a world beyond physics. Darwin taught that new species drive wedges into the crowded floor of nature to make room for their own existence. Yes, but no. Creatures, by existing, create the very conditions for other creatures to come into existence. Species constitute the very cracks in the floor of nature that constitute the niches for yet new species to come into existence, creating yet more cracks for still more species to spring forth. The blossoming biosphere creates its own ever-new possibilities of becoming, yet more diverse and abundant. The same holds almost unnoted for the exploding global economy. New goods create niches for yet further new goods. The invention of the World Wide Web created niches for selling on the web, hence eBay and Amazon, which in turn created content on the web, hence niches for search engines like Google, and for businesses that try to game the search algorithms to sell more stuff. Or think of all the iPhone apps and apps upon apps like the ad blockers that remove the sales pitches from what Safari shows. We stumble into the world we make possible as we lumber forward, with no or little insight or foreknowledge. I can go to East Sound to buy nectarines. We think that in physics, special and general relativity, quantum mechanics, and quantum field theory with the Standard Model, we will find the foundations from which we can derive the world, the ultimate becoming. We cannot. The ultimate may rest on the foundations, but it is not derivable from them. This ultimate and unknowable unfolding slips its foundational moorings and floats free. As Heraclitus said, the world bubbles forth. Chapter 1. The World is Not a Machine. Since the triumphs of Descartes, Newton, and Laplace, and the birth of classical physics, we have come to regard physics as the answer to our questions about what reality is. In that search, we have come to think of the world as a vast machine. This Newtonian fundamental framework is wonderfully extended by special and general relativity. Quantum mechanics and quantum field theory alter some of the basic deterministic aspects of classical physics, but not the view of reality as an enormous machine. My thesis in this book is that, with respect to an evolving biosphere, ours and any in the universe, the machine thesis is wrong. Evolving life is not a machine. Elaborating how this is so will require some patience on all our parts. The consequences of the change in worldview here proposed cannot be anticipated, but I hope they will include the realization that we are members of a living world of untellable creativity in its becoming. Along with that, I hope, will come a profound joy, an expanded awareness, a heightened appreciation, and a deepened sense of responsibility for the living world. Time will tell. C.P. Snow wrote his famous essay, The Two Cultures, decrying the split between the world of science and the world of art. Part of this split is the distinction between mute matter and the human imagination. But between these stands the evolving living world, whether dumb of awareness or broadly conscious. I hope to show you that, unlike physics where laws hold sway, no laws at all entail the becoming of the biosphere. No one knows or can know what shall become as the biosphere evolves and shapes its own future in ways we cannot state in advance. They are unprestatable. This lawless emergence, contingent yet not random, bespeaks a place between mute matter and Shakespeare. Life itself spans between physics and art. Please join me in exploring these issues, here hardly stated. There is much to do, more than this book can hope to accomplish, but I will try to give us a good start. The non-ergodic universe above the level of atoms. Has the universe made all the possible types of stable atoms? Yes. Bosons and fermions, the two broad kinds of particles physics knows, have glommed together in every conceivable combination to yield the 100-odd elements that make matter. But will the universe make all possible complex things? No, not at all. Most complex things will never get to exist at all. It is easy to see why. Proteins are linear sequences of 20 kinds of amino acids: alanine, phenylalanine, lysine, tryptophan, and so forth. The specific sequence of these 20 amino acids along the main chain of a specific protein, linked by peptide bonds, defines the primary sequence of that protein. Thereafter, the protein folds in complex ways to perform its functions in the cell. A typical protein in humans is a linear sequence of some 300 amino acids. Some proteins are thousands of amino acids long. How many possible proteins are there with only 200 amino acids in each? There are 20 choices at each position, so the total number of possible proteins of length 200 is 20 raised to the 200th power. That is about 10 raised to the 260th power. This is a hyper-astronomical number. The next point is to see that the universe cannot have made more than a very small fraction of these possible proteins in the time since the Big Bang. By our best reckoning, the age of the universe is about 13.7 billion years, which is about 10 to the 17th seconds. There are an estimated 10 to the 80th particles in the known universe. Quantum mechanics tell us that the shortest span of time in which anything can happen in the universe is the Planck time, 10 to the minus 43rd seconds. So, if the 10 to the 80th particles in the universe were doing nothing since the Big Bang, except making proteins in parallel at every tick of the Planck time clock, it would take 10 to the 39th power times the 13.7 billion year actual history of the universe to make all possible proteins of the length 200 amino acids just once. In contrast, it may have taken only a few billion years to make all 20 amino acids. The universe, whatever might happen, can have made only a tiny fraction, 1 over 10 to the 39th, of the possible proteins, each consisting of 200 amino acids. History enters when the space of the possible is vastly larger than what can become actual. For example, the evolution of life itself is a profoundly historical process. So too may be space chemistry and the formation of complex molecules. Thus, the becoming of the universe above the level of atoms is a historical process. The physicist's phrase for this historicity is non-ergodic. Ergodic means, roughly, that the system visits all its possible states over some reasonable time period. The central example from equilibrium statistical mechanics is a liter volume of gas falling to equilibrium rapidly. The gas particles darting about in the bottle assume nearly every possible configuration before settling into the stablest possible state. But non-ergodic means that a system does not visit all its possible states, like the amino acids that cannot make all possible proteins even after an astronomical number of repetitions of the 13.7 billion year history of the universe. If we ask whether the universe has created all stable atoms, the answer is yes. So the universe is roughly ergodic with respect to atoms, but it is not ergodic with respect to complex molecules. And the more complex the class of molecules, the more sparsely can that class have been sampled since the Big Bang. Consider proteins of length n equals 1, 2, 3, 4, and so forth up to n plus 1 amino acids. As n increases, the universe samples the possible sequences ever more sparsely. The universe can explore and surge upward in complexity indefinitely. In this sense, there is an indefinite sink upward in complexity. The universe can explore indefinitely vast realms. Beyond the second law. The second law of thermodynamics states that disorder tends to increase. Disorder is measured as entropy. The canonical case again is that of a closed thermodynamic system of gas particles exploring every possible configuration in a liter container before settling into a state of equilibrium. It has reached what is called the most probable macrostate, the state of maximum entropy. The second law insists that entropy tends to increase as a system flows from less to more probable macrostates, like a steaming cup of coffee cooling to lukewarm and then cold, or like a cube of ice melting to a puddle. But if everything moves inevitably toward a maximum state of entropy, then how can the universe, and especially the biosphere, be enormously complex? We really do not know. Part of the reason is that the universe itself is still on its way to equilibrium, the homogeneous murk that cosmologists call heat death, and that the biosphere is not a closed system. The sun shines on us, providing energy to build complexity, forestalling entropy, but only for a while. A deeper part of the reason may be that the universe cannot exhaust complexity. Indefinite upward exploration into the vast possibilities of complexity occurs in terms of the complexity of space chemistry and the burgeoning diversity of the biosphere. Thus, we must ask how this indefinite complexity sink may bear on the emergent complexity of the universe. In particular, the biosphere has become complex with teeming diversity since its origin on Earth 3.7 billion years ago. Presumably, this would be true of other living biospheres in the universe. Something in living biospheres surges upward in diversity and complexity. But how and why does it? I hope to show you at least part of the source of this surging, a non-equilibrium companion of the famous second law, a principle that would help explain how the biosphere today can be far more complex than it was 4 billion years ago. Space chemistry shows this surging upward in complexity. After the Big Bang, the stable elements were created. The Murchison meteorite, formed some 5 billion years ago, has on the order of 14,000 types of organic molecules cooked up from the elements of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The evolving biosphere manifests this surging upward in complexity from protocells 3.7 billion years ago to the millions of species now. We seek nothing less than an understanding of where this order came from. The order is historically contingent, yet not fully random. Witness the order among the higher taxa as life explores the vast diversity of Darwin's forms most beautiful. The biosphere literally constructs itself and does so into a biosphere of increasing diversity. Again, how and why is this? Remarkably, the answer may be because the living world can become more diverse and complex and in an ongoing way creates its own potential to do so. That requires harnessing the release of energy to build order faster than that order can be dissipated by the second law of thermodynamics. As we will see, Montevielle and Mosius's beautiful theory of constraint closure and thermodynamic work cycles figure prominently in our new story. Why do human hearts exist? Among the universe's endlessly unspooling complexities is the human heart. The universe in its lifetime can generate but a tiny fraction of all the possible proteins and even a tinier fraction of the tissues that are made from proteins and, in turn, make up the organs that we call hearts. So here is the question. Why do human hearts exist in this non-ergodic universe that exists above the level of atoms? Roughly, human hearts exist because they pump blood and thus were of selective advantage in our vertebrate ancestors and were inherited by us. In short, Darwin gives us part of the answer. Hearts help us survive and so are selected. But Darwin did not realize that he was also giving a deeper account of why hearts exist at all. Given ongoing, evolving life with reproduction and heritable variation, if an organ arose with even a glimmering of the functional capacity to pump blood, that happy accident could be selected in organisms just a bit too large for simple diffusion to transport needed oxygen to every one of their cells. In short, hearts exist in the non-ergodic universe above the level of atoms by virtue of their functional role in abetting the survival of living, evolving organisms having such hearts. As they replicate, organisms propagate their organization of process, the way all of these pieces fit and work together. Organs are parts of that organization and exist for and by means of the whole heart. Hearts exist, in other words, because life exists. Moreover, as we will see, life creates the expanding space of possibilities into which it evolves in the non-ergodic universe above the level of atoms. That is the first major conclusion of this book. For complex things, getting to exist at all in the non-ergodic universe above the level of atoms needs explanation, and the answer is as simple as it is profound. Human hearts exist by virtue of their functional role in sustaining the existence, hence the evolving future, of living organisms with such hearts. Organisms propagate above the level of atoms, and so with them do their sustaining organs. Hearts exist in the non-ergodic universe above the level of atoms because organisms need functioning hearts to exist and proliferate. As Kantian wholes, organisms carry along with them their sustaining parts. Organisms with hearts exist, so hearts exist. Why do eyes exist, noses exist, kidneys exist, tentacles with suckers on them exist, sex exist, parental care exist, and the giraffe's long neck exist? The answer is the same. By virtue of the roles these organs and processes play in abetting the survival of the evolving, persistently living organisms having these organs and properties. They too exist for and by means of the whole. All these aspects of our universe exist on a single blue dot planet. If life is abundant among the estimated 10 to the 22nd solar systems in the universe, what myriad of complex things, unpredictable and perhaps unthinkable, lies in the indefinite reach upward in complexity even further above atoms? What is an organism? Long before Darwin, Immanuel Kant understood this. An organized being, then, has the property that the parts exist for and by means of the whole. Call this a Kantian whole. The heart exists for and by means of the whole organism of which it is a functioning part. Humans are Kantian wholes. A simple example of a Kantian whole is noted in one example. It is a hypothetical example of what I call a collectively autocatalytic set. It consists of polymers like the small proteins called peptides. This system will be of central interest to us in this book. It begins with simple food molecules, single building blocks we will call A and B, the monomers, and the four possible dimers, AA, AB, BA, and BB, all of which are supplied from the outside. Then there are longer polymers, such as ABBA and BAB, formed from this food set through reactions combining two polymers end to end to create a longer polymer, or breaking a longer polymer into two fragments. But here is the important idea. The reactions forming these longer products are catalyzed by the very polymers that make up the system. The system is collectively autocatalytic. A simpler example consists of two small polymers, AB and BA, each formed by a reaction linking A and B. Here, AB catalyzes the reaction forming BA, and BA catalyzes the reaction forming AB. The set is collectively autocatalytic. In a set, no polymer catalyzes its own formation. Rather, the set as a whole catalyzes its joint formation. If one considers catalyzing a reaction a catalytic task at all, the tasks are jointly realized in a kind of catalytic task closure. Such a system is a whole and more than the sum of its parts. The closure of mutual catalysis is not seen in any of the parts alone. Rather, the closure is a collective property. This system can literally build itself and reproduce. It is a Kantian whole with parts that exist for and by means of the whole. It shall be my central model for the origin and even the character of life. Collectively autocatalytic sets emerge spontaneously in sufficiently diverse chemical soups. Such systems exist, made of peptides, of RNA, and of DNA. I believe such systems may have been essential to the origin of life, and will discuss this in detail later. Two Chilean scientists, Humberto Maturana and Francisco Varela, introduced the idea of autopoiesis, a system that makes itself. A collectively autocatalytic set is an example of an autopoietic system. All free living systems are autopoietic, collectively autocatalytic systems. If capable of heritable variation, such systems can undergo natural selection and form evolving biospheres. We do not live alone. We make our living world together. No individual is alive alone. We are all joined together in the evolving, emerging, unfolding of the biosphere as a whole. We are the conditions of one another's existence. Thus we all get to exist for long periods of time in the non-ergodic universe above the level of atoms. Our biosphere has propagated stably for some 3.7 billion years. These issues take us beyond our physics-based view of the world. Brilliant physicist Steven Weinberg voiced the physicist's thoughts. 1. The explanatory arrows always point downward from social systems to people to organs to cells to biochemistry to chemistry and finally to physics. 2. The more we know of the universe, he wrote, the more meaningless it appears. Yes, but we loudly say no to these claims. We begin to see in this book that what gets to exist in the non-ergodic biosphere above the level of atoms, hearts, sight, smell, exists by virtue of the functional roles these systems and subsystems play in abetting the survival and further evolution of the organisms of which they are parts. Hearing arose by co-opting the evolution of jaw bones that were sensitive to vibration in an early fish and became the incus, meles, and stapes of our middle ears. No one could have said 3 billion years ago that hearing would evolve. We could not have pre-stated that evolutionary emergence. But middle ear bones now exist in the non-ergodic universe above the level of atoms by virtue of their emerged functional role in the survival and evolution of organisms having hearing. The explanatory arrows do not point downward from hearing to physics, but upward to the selection of organs that abet hearing. That selection acted at the level of whole organisms as hearing evolved. That is why such organs exist in the universe, and Weinberg is just wrong. I will return later to our incapacity to pre-state the emergence of hearing, for from this it will follow that no laws at all entail the evolution of the biosphere, and that reductionism, Weinberg's dream of a final theory, is false. The world as machine. Prior to Descartes and Newton, the Western mind saw a cosmos, an organic whole of which we were members. This was the view of the Church. With his res cogitans, Descartes reserved mind stuff for humans. The rest of the world, including our bodies and all animals and plants, were res extensa, extended stuff, mechanism. With the Principia of Newton, Aristotle's 4 causes, formal, final, efficient, and material, dwindled to a mathematized version of efficient cause. Newton's differential and integral calculus as captured in his 3 laws of motion and universal gravitation. Laplace's demon, knowing the positions and momenta of all the particles in the universe, could calculate its entire past and future. The world became a huge machine in classical physics with its honest orbits. Modern reductionism was born. The theistic God retreated to a deistic God who set the universe up, selected initial conditions, and let Newton's laws take over. This God could no longer act in the world to create miracles. The struggle between science and religion flowered, and the rebellion of the Romantics followed. It was science with its rule and line, wrote Keats dismissively. Weinberg is of this tradition. The scientific world is a machine and quite without meaning, a blight on Shakespeare and your natterings. How overbold this is. The issues here have to do with including the towering problems of consciousness and agency, both vacant from the machine picture. How overbold indeed. One thing missing in the world, according to physics, is the crucial idea of agency, which will concern us in a later chapter. Given agency, meaning exists in the universe, Weinberg or not. We are agents playing our complex filigreed games with one another. Rocks play no games. Then what must a system be to be an agent? What must systems be to evolve complex interwoven games of life with one another? This complexity is part of the complexity of the universe. But leave out for now the magisterial issue of consciousness. Even if the biosphere were organisms dumb of consciousness, evolution would in no way be a world machine. In the non-ergodic universe above the level of atoms, the biotic world surges beyond our saying, beyond equations and calculation in Laplace's style, beyond Keats's rude rule and line, and into the exploding adjacent possibilities life itself creates. The evolving biosphere becomes sucked into the very opportunities to explore untellable reaches of complexity, of never-before-seen organizations of matter and energy, life evolving. This evolution of the biosphere is an organic whole. Its members jointly create the very pathways of further becoming what the biosphere as a whole shall be.
Sample complete. Ready to continue?